Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on November 26, 2025, about 3 days ago. It shows that a compact 3D trace-based world model can learn robot manipulation skills from just 5 short videos, reaching about 80% success on several real robot tasks, and about 68% success even when learning only from a handful of uncalibrated human phone videos. The paper is titled TraceGen, World Modeling in 3D Trace Space Enables Learning from Cross-Embodiment Videos. And as we will see later, the implications for cross-embodiment robot learning are quite significant. Alright, Figure 1 lays out the whole story, from raw videos to a world model that outputs actionable 3D traces. The top panels show TraceForge turning 123,000 mixed human and robot videos into 1.8 million aligned image, depth, and language triplets, while TraceGen converts those into 3D motion traces. The bottom left graph shows that, after just 5 robot warm-up videos, the warmed-up model reaches about 80% success and is many times faster than video world models. The bottom right panels illustrate human-to-robot transfer, where 5 casual phone videos still yield about 68% success on real robot executions. Well, Figure 2 breaks down where all those training videos actually come from. The central donut chart shows that about 64% of the corpus is robot video, and about 36% is human video, so the model mostly watches robots but still gets a large dose of human demonstrations. The outer ring labels major sources like Agibot, Droid, Bridge V2, RoboMimic, Epic Kitchen, and SSV2. These span tabletop lab setups, egocentric head-mounted views, and messy in the wild kitchens, which together encourage generalization across embodiments and scenes. Alright, Figure 4 zooms into how TraceForge actually converts a raw video into a clean 3D trace. The left film strip shows the input video being cut into task-relevant chunks, which then feed both language instruction generation and geometry estimation. The central blocks estimate camera pose, depth, and 3D point tracks, and these are combined through unprojection into a raw 3D trajectory cloud. On the right, roll to camera alignment and speed retargeting, refine that cloud into a normalized 3D trace that is ready for TraceGen training. So while Figure 4 described how TraceForge builds traces, Figure 5 explains how TraceGen turns raw inputs into future motion. The left side shows language, color images, and depth maps going through frozen text and vision encoders to become unified visual tokens. These tokens feed a flow-based model that learns a velocity field, so it gradually denoises random noise into key point motion patches over time. The right side illustrates how those patches unpatch into 3D trajectories in the camera frame, which then drive the robot through inverse kinematics controllers. Alright, Figure 7 translates that modeling pipeline into real robot performance. The 4 left panels plot each task, and the right panel aggregates them, showing success rate on the vertical axis and predictions per minute on the horizontal axis. TraceGen consistently sits in the top right, which means it is both accurate and fast. Video world models cluster lower and further left, so they are either slower, less successful, or both. This gap matters because it shows that planning directly in 3D trace space gives practical, real-time few-shot control on real hardware. So while Figure 7 highlighted speed and success with robot warm-up videos, Figure 8 focuses on human-to-robot skill transfer. The bar chart shows that fine-tuning from the pre-trained model reaches about 68% overall success from just 5 handheld human videos, with task scores between 40 and 80%. The blue bars, which represent training from scratch on the same human data, stay at 0 for every task. This contrast shows that large-scale cross-embodiment pre-training is crucial for making noisy human phone demos actually useful for robot control. So after those human-to-robot transfer results, Table 2 digs into where pre-training data actually comes from and how much it matters. The table compares 4 setups that all get the same 5 warm-up videos, from scratch, human SSV2 only, robot Agibot only, and the full TraceForge 123,000 mix. From scratch fails completely, with 0 successes, while SSV2 reaches about 25% and Agibot about 45%. The mixed human and robot TraceForge data jumps to 70% success, which shows that both robot embodiment coverage and human motion diversity are crucial for strong transfer. So to wrap up, 2 ideas stand out. Predicting in 3D trace space gives robots a fast, compact world model, and large-scale cross-embodiment pre-training turns messy human and robot videos into transferable skills from just a few demos. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.